I want you to imagine you're a tiny ant just crawling through the grass under an apple tree back in the year 1666. Now, to you, the world is absolutely enormous, right? Every falling object is a potential disaster. And on this particular sunny afternoon, you're about to get a front row seat to one of the most famous events in scientific history from a totally unique point of view. Just picture the sudden terror. Out of nowhere, a giant red apple snaps from its branch and plunges directly toward you, slamming into the earth just inches from your tiny antennae. As you shake off the dust, you're probably wondering what unseen hand just hurled that fruit at you. Well, interestingly enough, that exact same near miss sparked a brilliant question from the giant human sitting just a few feet away. You know him, a young scientist named Isaac Newton. He watched that very apple fall, and he asked a beautifully simple yet literally universe-altering question. Why did that apple fall down instead of sideways or, upward? Newton realized pretty quickly there wasn't some giant physical hand pushing the apple. It was an invisible force pulling it toward the earth. He called this force gravity. But his genius didn't just stop there in the grass. He looked up at the daytime sky and brilliantly wondered, hey, if the Earth has this invisible force pulling on an apple, does it reach all the way out into space? Does this exact same force keep the moon going around the Earth? And the answer he arrived at was a massive, resounding yes. Now, before we get too far, we need to clarify two terms that get mixed up all the time. To our surviving ant, the difference doesn't matter one bit, but in physics, it's absolutely crucial. Gravity refers to the specific pull of a planet, like the Earth, on an object near its surface, like that terrifying apple. Gravitation, on the other hand, is the universal force of attraction between literally any two masses anywhere in the cosmos, like the massive sun pulling on the Earth. So gravitation is the whole universal shebang. Newton actually wrote a mathematical formula to calculate this universal pull, and it all comes down to mass and distance. It breaks down into three super simple rules. First, a bigger mass equals a bigger force. Second, a closer distance equals a bigger force. That's exactly why our tiny ant feels the Earth pull so incredibly strongly right there in the dirt. And third, the farther away you get, the weaker the force becomes. It's why astronauts way out in deep space feel almost no gravitational pull at all. Let's bring it back down to the ant's perspective for a second. When that massive apple dropped, it didn't just casually drift down. It sped up as it fell. This speeding up is called acceleration due to gravity, and here on Earth's surface, it has a very specific constant value, 9.8 meters per second squared. This relentless downward acceleration is the terrifying reality of Earth's gravity for our little ant friend, because it means the longer an object falls, the faster and harder it's going to crash. And this perfectly sets up a totally mind-blowing aspect of gravity. If you took that heavy apple and, say, a light feather, or even our tiny ant, and dropped them from the exact same height in a vacuum with absolutely zero air resistance, gravity would accelerate them all equally. No kidding. They would all speed up at exactly 9.8 meters per second squared and hit the ground at the exact same time. In everyday life, a feather or a falling ant only falls slower because the air catches them and pushes back, not because the Earth is pulling on them any less. Okay, this brings up a fundamental cosmic rule, and it's the difference between the actual stuff you're made of and how hard gravity pulls on that stuff. Your mass is the fixed amount of matter in your body, and we measure that in kilograms. It never, ever changes, whether you are an ant crawling in England or an astronaut floating in deep space. But your weight, which is measured in newtons, is the actual force of gravity pulling on that mass. Because gravity changes depending on where you are in the universe, your weight is entirely dependent on your current location. Let's paint a clearer picture of this. Imagine comparing a human standing on Earth to that exact same human standing on the moon. If a 60-kilogram person stepped onto the lunar surface, their mass, again, the actual matter making up their body, would stay exactly the same at 60 kilograms. But the weight they feel, that changes completely. The downward force drops dramatically, plummeting from 588 newtons on Earth to just 96 newtons on the moon. So why this dramatic weight loss? Well, remember that acceleration number on Earth, 9.8 meters per second squared? On the moon, the acceleration due to gravity is a tiny 1.6 meters per second squared. Since the moon has significantly less mass than the Earth, its gravitational pull is just much weaker. This literally means you would feel about 6 times lighter bounding around on the lunar surface than you do sitting in your living room right now.
All right, let's put our ant narrator back in the grass at Wilstorp Manor, looking up at the night sky. The ant knows for a fact the Earth pulls downward. I mean, it barely survived the apple to prove it. And Newton just realized the Earth also pulls on the moon. So naturally, the ultimate terrifying question arises. If Earth's gravity is constantly pulling on that giant rock in the sky, why in the world doesn't the moon fall down and crush us all?
Here is the amazing truth of planetary physics. The moon actually is falling. It is constantly, endlessly falling toward the Earth. But it never hits us because it's also moving sideways at an incredibly fast speed. These two motions, the downward pull of gravity and that sheer sideways momentum, they balance out perfectly. So instead of a catastrophic world-ending collision, this creates a continuous curved path around the Earth. That continuous falling, that is exactly what an orbit is. Think of it like swinging a ball on a string around your head. The string acts exactly like gravity. It's constantly pulling the ball inward. Meanwhile, the sheer speed of the ball makes it want to fly straight away. As long as you keep swinging, it travels in a perfect circle. But if you were to suddenly grab a pair of scissors and snip that invisible gravitational string, the balance breaks immediately. The moon would instantly fly off in a straight line, abandoning Earth to just drift out into deep space. We actually have modern examples of this exact same principle happening right above our heads today. Human astronauts living inside the International Space Station experience this exact same continuous freefall. When you see them floating around on video looking completely weightless, it isn't because there's no gravity up there. Earth's gravity is absolutely still pulling them down. But the space station is moving sideways so incredibly fast, we're talking about 17 times faster than a speeding bullet, that as they fall, the curve of the Earth literally drops away out from under them. They are moving fast enough to constantly miss the ground. But what if you don't want to just stay in orbit? What if you want to completely break free from this gravitational string and travel out into deep space? Well, to pull that off, an object must reach something called escape velocity. This is the absolute minimum speed you need to hit to break the grip of a planet's gravity once your rocket engine shut off. Go any slower, and you're either going to fall back down or get trapped in orbit forever. Hit this exact speed, and you escape entirely. Different planets have vastly different gravitational grips, as you can probably guess. To escape the moon, you only need to travel at 2.4 kilometers per second. But a rocket leaving Earth, it needs to hit a blistering 11.2 kilometers per second. To really put that into perspective, a rocket has to travel over 12 times faster than a commercial jet airliner just to leave home. And if you somehow tried to launch off the massive planet Jupiter, you'd face a truly staggering escape velocity of nearly 60 kilometers per second. It is truly fascinating to step back and realize that the exact same force that threatened our tiny ant with a falling apple way back in 1666 is the very same universal force that holds the moon in its orbit and binds the entire cosmos together. Every single piece of mass in the universe is connected by these invisible gravitational strings, which leaves us with one final, absolutely awe-inspiring thought to take away from this explainer today. If gravitation truly connects every single object everywhere, what distant, massive forces out in the universe are secretly pulling on you right at this very moment?